previous chapter, we have discussed about various aspects linked to spatial data analysis. In this chapter, we will get to understand about different spatial analysis types like vector-based analysis, raster-based analysis, grid-based spatial analysis. Vector-based spatial data analysis. In this section, the basic concept of various vector operations are dealt in detail. They are multi-layer operations which allow combining features from different layers to form a new map and give new information and features that were not present in the individual maps. Topological overlays. Selective overlay of polygon, lines and points enables the user to generate a map containing feature and attribute of interest extracted from different themes or layers. Overlay operation can be performed on both raster, that is grid, and vector maps. In case of raster maps, calculation tool is used to perform overlay. In topological overlays, polygon feature of one layer can be combined with point, line and polygon feature of the layer. Polygon in polygon overlay. Output is a polygon coverage. Coverages are overlaid 2 at the time. There is no limit on the number of coverages to be combined. New file attribute table is created having information about each newly created feature. Line in polygon overlay. In this overlay, the output is a line coverage with additional attribute data. No polygon boundaries are copied in this overlay. New arc node topology is created. Point in point overlay. In this overlay, the output is a point coverage with additional attribute data. No new point features are created in this overlay. No polygon boundaries are copied. Logical operators. Overlay analysis manipulates spatial data organized in different layers to create combined spatial features according to logical condition specified in Boolean algebra with the help of logical and conditional operators. The logical conditions are specified with operands, that is nothing but the data elements, and operators are indicated by the relationships among the data elements. In vector overlay, arithmetic operations are performed with the help of logical operators. There is no direct way to it. Common logical operators include AND, OR, XOR, that is nothing but exclusive OR, and NOT. Each operation is characterized by a specific logical checks of decision criteria to determine if a condition is true or false. The table shows the true or false conditions for the most of the common Boolean operation. In this, A and B are the two operands. 1 implies true condition and 0 implies a false condition. Thus, if a condition is true while the B condition is false, then the combined condition of A and B is false, whereas the combined condition of A or B is true. And is used for common area, intersection, clip operation. OR is used for union or addition. NOT is used for inverter. Exclusive or it is called as XOR, is used for minus operations. The most common basic multi-layer operations are union, intersect and identify operations. All three operations merge spatial features on separate data layers to create new features from the original coverage. The main difference among these operations is in the way spatial features are selected for processing. Overlay operations. There are different types of vector overlay operations and gives flexibility for geographic data manipulation and analysis. In polygon overlay, features from two map coverages are geometrically intersected to produce a new set of information. Attributes for these new features are derived from the attributes of both the original coverages, thereby contain new spatial and attribute data relationships. One of the overlay operation is AND or intersect in vector layer operation, in which two coverages are combined. Only those features in the areas common to both are preserved. For example, A and B are present. So, AND is a feature where it combines both the elements in A component and both the elements in B component, and it creates a new map where it contains both the elements of A and B. Feature attributes from both coverages are joined in the output coverage. Raster based spatial data analysis. Present section discusses the operational procedures and quantitative methods for the analysis of spatial data in raster format. In raster analysis, geographic units are regularly spaced and the location of each unit is referred by rows and column position. Because geographic units are equal size and identical shape, area adjustment of geographical units is unnecessary and spatial properties of geographic entities are relatively easy to trace. All cells in a grid have a positive position reference following the left to right and top to bottom data scan. Each cell in a grid is an individual unit and must be assigned a value. Depending on the nature of the grid, the value assigned to the cell can be an integer or a floating point. When data values are not available for particular cells, they are described as no data cells. No data cells differ from cells containing 0 in the sense that 0 value is considered to be a data. The regularity in the arrangement of the geographic units allows for the underlying spatial relationships to be efficiently formulated. For instance, the distance between the orthogonal neighbors, that is nothing but the neighbors on the same row or the neighbors on the same column, is always a constant, whereas the distance between two diagonal units can also be computed as a function of that constant. Therefore, the distance between any pair of units can be computed from the difference in the rows and column position. Furthermore, directional information is readily available for any pair of origin and destination cells as long as their position in the grid are known. Advantages of using the raster format in spatial analysis. Efficient processing. Because geographic units are regularly spaced with identical spatial properties, multiple layer operation can be processed very efficiently. Numerous existing sources. Grids are the common format for numerous sources of spatial information, including the satellite imagery, scanned aerial photographs and the digital elevation model, among others. These data sources have been adopted in many GIS projects and have become the most common sources of major geographic database. Different feature types organized in the same layer. For instance, the same grid may consist a point feature, a line feature or an area feature, as long as the different features are assigned different values. Grid format disadvantages. Data redundancy. When data elements are organized in a regular spaced system, there is a data point at the location of every grid cell, regardless of whether the data element is needed or not. Although several compression techniques are available, the advantage of gridded data are lost whenever the gridded data format is altered through compression. In most cases, the compressed data cannot be directly processed for analysis. For example, you have different techniques for compressing your photographs. Whenever you are trying to compress the photographs, the pixel value of that cell is being decreased. As a result, the clarity of the image is being decreased. Instead, the compressed raster data must be first be decompressed in the order to take the advantages of the spatial regularity. Resolution confusion. Gridded data give an unnatural look and unrealistic presentation unless the resolution is sufficiently high. Conversely, spatial resolution dictates spatial properties. For instance, some spatial statistics derived from a distribution may be different if spatial resolution varies, which is result of well-known scale problem. For example, if large amount of area is being represented in the raster format where very less amount of cells are representing large amount of data, then in this such situation the resolution is being missed or the resolution is being varying. Whenever the resolution is very much high, all the data on the map can be easily represented in the raster format. Cell value assignment difficulties. Different models of cell value assignment may result in quite different spatial patterns. Grid operations used in map algebra. Common operations in grid analysis consist of the following operations, which are used in map algebra to manipulate the grid files. The map algebra language is a programming language developed to perform cartographic modeling. Map algebra performs the following 4 basic operations. Location functions that work on every single cell. Focal function that process the data of each cell based on the information of the specified neighborhood. Zonal functions. This provides the operation that works on each group of cells of identical values. Global functions that work on a cell based on the data of the entire grid. Local functions process a grid on a cell by cell basis, that is, each cell is processed based on solely on its own value without referring to the values of the other cells. In other words, the output value is a function of the value or the values of the cell being processed, regardless of the values of the surrounding cell. For a single layer operation, a typical example is changing the value of each cell by adding or multiplying a constant. When there is no data for a cell, the corresponding cell of the output grid remains blank. For example, a raster cell is being used. In this raster cell, many cells are having values and some cells may not be having a value. So, the output image is that the cells which are having value will be represented in the output cell, or it will be multiplied or subtracted, but whereas the cells which are having blank, they remain as a blank in the output value. Trigonometric, exponential and logarithmic and logical expressions are all acceptable for defining local functions. Focal functions. Focal function processes cell data depending on the values of neighboring cells. For instance, computing the sum of the specified neighborhood and assigning the sum to the corresponding cell of the output grid is the focal sum function. A 3 by 3 kernel defines neighborhood. For cells closer to the edge where the regular kernel is not available, a reduced kernel is used and the sum is computed accordingly. For instance, a 2 by 2 kernel adjusts the upper left corner cell, thus the sum of the 4 values is 2, 0, 2 and 3, and this yields the value of 7, which becomes the value of the cell in the output grid. The value of the second row, second column is the sum of the 9 elements that is present 2, 0, 1, 2, 3, 0, 4, 2 and 2, and the sum equals to 16. Another focal function is the mean of the specified neighborhood, the focal mean function. Other commonly employed focal function include standard deviation, that is nothing but the focal standard deviation, the maximum, focal maximum, the minimum, that is the focal minimum, and the range, that is focal range. Zonal functions. Zonal function processes the data of the grid in such a way that the cell of the same zone are analyzed as a group. A zone consists of a number of cells that may or may not be contiguous. A typical zonal function requires 2 grids, a zone grid which defines the size, shape and location of each zone, and a value grid which is to be processed for analysis. In the zone grid, the cells of same zone are coded with same value, while the zones are assigned different zone values. The objective of this function is to identify the zonal maximum for each zone. The procedure involves finding the maximum value among these cells from the value grid. Typical zonal functions include zonal mean, zonal standard deviation and zonal sum, zonal minimum, zonal maximum, zonal range and zonal variety. Other statistical and geometric properties may also be derived from additional zonal function. For example, the zonal perimeter function calculates the perimeter of each zone and assigns the returned value to each cell of the zone in the output grid. Global functions. For global functions, the output value of each cell is a function of the entire grid. As example, the Euclidean distance function computates the distance from each cell to the nearest source cell, where the source cell are defined in an input grid. In a square grid, the distance between two orthogonal neighbors is equal to the size of a cell or the distance between the centroid location of the adjacent cells. Likewise, the distance between two diagonal neighbors is equal to the cell size multiplied by the square root of 2. Distance between non-adjacent cells can be computed according to their rows and column addresses. Another useful global function is the cost path function, which identifies the least cost path from each selected cell to its nearest source cell in terms of cost distance. These global functions are particularly useful for evaluating the connectivity of a landscape and the proximity of a cell to any given entities. Some important raster analysis operation. In this section, some of the important raster based analysis are dealt. The renumbering is used in areas where we have been found in the grid file. Then, performing a cost surface analysis, performing an optimal path analysis, performing a proximity search. Area numbering. Area numbering assigns a unique attribute value to each area in specified grid file. An area consists of two or more adjacent cells that have the same cell value or a single cell with no adjacent cell of the same value. To consider a group of cells with the same value beside each other, a cell must have a cell of the same value on at least one of its sides horizontally or vertically, that is nothing but 4 connectivity on either of the 4 sides, or on at least one side horizontally, vertically or diagonally, that is nothing but 8 connectivity. One can renumber all of these areas in a grid, or you can renumber only those areas that have one or more specific values. If you renumber all the analysis area, area number assigns a value of 1 to the first area located. It then assigns a value of 2 to the second area and continues this reassignment method until all the areas are renumbered. When you renumber area that contain a specific value such as 13, the first such area is assigned the maximum grid value plus 1. For example, the maximum grid value is 25. The number of assign a value of 26 to the first area, a value of 27 to the second area, and continues until all the areas that contain a specified value are renumbered. Cost surface analysis. Cost surface generates a grid with each grid cell representing cost to travel to that grid from the nearest one or more start location. The cost of traveling to a given cell is determined from a weight grid file. Zero weights option uses attribute value of 0 as the start location. By row column option, they use the specified row and column location as the start location. Optimal path. Optimal path lets us analyze a grid file to find the best path between the specified location and the closest to start location as used in generating a cost surface. The computation is based on a cost surface file that you generate with cost surface. One must specify the start location by rows and columns. The zeros in the input cost surface represents 1 in the end point. The specified start location represents the another end point. Testing the values of the neighbor cells for the smallest value generates the path. When the smallest value is found, the path moves to that location, where it repeats the process to move the next cell. The output is a path of least resistance between 2 points with least expensive but not necessarily the straightest line between 2 endpoints. The output file consists of only the output path attribute value, which can be optionally specified surrounded by void values. A proximity search. Proximity lets you search a grid file for all the occurrences of a cell value or a feature within either a specified distance or a specified number of cells from the origin. You can set both the origin and the target to a single value or a set of values. The number of cells to find can be limited. For example, if you specify to find 10 cells, the search stops when 10 occurrences of the cell have been found within the specified distance of each origin value. If you do not limit the number of cells, the search continues until all the target values are located. The output grid file has the user type code and the data type code of the input file. The grid cell values in the output file indicates whether the grid cell corresponds to an original value. The value searched for and located within the specified target or either of these. The origin and the target values may be retained as the original values or specified to be another value. Grid-based spatial analysis. Diffusion modeling and connectivity analysis can be effectively conducted from grid data. Grid analysis is suitable for these types of problems because the grid's regular spatial configuration of geographic units. Diffusion modeling. It deals with the process underlying spatial distribution. The constant distance between the adjacent unit makes it possible to stimulate the progression over geographic units at a consistent rate. Diffusion modeling has a variety of possible applications, including wildfire management, disease vector tracking, migration studies, and innovation diffusion research, among others. Connectivity analysis. Connectivity analysis evaluates inter-separation distance, which is difficult to calculate in a polygon coverage, but can be obtained much more effectively in a grid. The connectivity of a landscape measures the degree of which surface features of a certain type are connected. Landscape connectivity is an important concern in environmental management. In some cases, effective management of natural resources requires maximum connectivity of specific features. For instance, a sufficiently large area of dense forest must be well connected to provide a habitat for some endangered species to survive. In such cases, forest management policies must be set to maintain the highest possible level of connectivity. Connectivity analysis is especially useful for natural resource and environmental management. GIS is considered a decision-making tool in problem-solving environment. Spatial analysis is a vital part of GIS and can be used for many applications like site suitability, natural resource monitoring, environmental disaster management, and many more. Vector, raster-based analysis functions and arithmetic, logical, and conditional operation are covered based on the recovered derivations.